Hi, question number 3 asks you to explain the underlying causes of the hydrophobic effect. Well, the hydrophobic effect, all right, what is it, first of all? Though the hydrophobic effect is that nonpolar molecules tend to clump together and get away from water. They tend to come out of solution and clump together, right? So the classic example, the hydrophobic effect is if you pour oil into water, the two separate into different layers, and the hydrophobic molecules tend to accumulate. All right, well, why is this? Well, it's because if we're going to take a nonpolar molecule, so draw some hydrocarbon here, if we're going to take this and dissolve it into water, all right, the same thing has to happen to this nonpolar molecule that has to happen to any other molecule that we're trying to dissolve in water. Well, it has to get surrounded by water molecules. Right. I'm just going to draw them as a bunch of dots here. Right. These will be all our water molecules. Right. So there are actually attractive forces between water molecules and our nonpolar solute here. All right, because we have London dispersion forces that are occurring between the water molecule and the nonpolar solute. So this is an attractive interaction. Now, what happens though if we bring multiple of these large hydrophobic molecules together and they're both surrounded by water molecules? Well, I'll draw just a few more of these waters. Right. Well, if we bring them together, all right, we're going to have to displace all of these water molecules here. They're going to have to go somewhere else in order to allow the two molecules to come together, or two hydrophobic molecules to come together. All right, now, when we made these two hydrophobic molecules together, they're still able to make London dispersion type interactions between them, right? So we haven't really changed the strength of the attractive forces that are around these hydrophobic molecules at all. But what we have done is all these water molecules in the middle here are now liberated. They're free. They're no longer locked into that clathoric cage around the nonpolar molecules. Well, so what are we doing here? We're increasing the randomness of the system. We're increasing the disorders. So entropy is increasing. Now, if entropy is increasing, this tends to drive down delta G, because if you remember the equation, delta G equals delta H minus T times delta S. Oops. And so having a large positive number for delta S because of this little negative sign here, oops, so that little negative sign tends to make a negative delta G. So the underlying cause of the hydrophobic effect is that the some of the water molecules that are locked into the clathoric cages get displaced when we start to aggregate hydrophobic molecules, and this increases the entropy of the system.